Welcome to EDU World Space.
This is chapter 21, problem number 88. As you can see in the figure, we have a point charge that is actually under the influence of an external electric field. Thus, there is an electric force acting on it. Thus, it is actually tilted towards right from its equilibrium position. This would be the equilibrium position, right? So the electric force acting on this charge has to be to the right so that it gets tilted towards right? So in this case, we're asked the magnitude of the charge, magnitude of point charge, which is basically Q, and the sign of it. Okay, we can answer one of these questions right now. So if we know the direction of the electric force from the figure, from the fact that it's tilted to the right, Fe equals Q times the electric field vector. So if the electric field vector is to the right, and force is also to the right, then Q has to be positive, right? So Q is a positive charge for sure, because if it were to be negative, then E and F would be anti-parallel. So if E showed the positive x direction, Fe would be acting along negative x direction. So for this case, the Q has to be positive. Now, how about the magnitude of it? So in order to find the magnitude, we're going to have to draw the free body diagram here, right? Free body diagram means show all the forces acting on the body that we're dealing with. And then since the body is in equilibrium, set the net force in the x direction to be equal to 0 and set the net force in the y direction to be equal to 0. So let's show all the forces acting on this charge. Like we said, the electric force is to the right. There is gravitational force F sub g downward always. And we have the string. This is a pendulum, so we have the tension, right? So let me go on a new page. We have the tension, the electric field, force due to the electric field, and F sub g, and we're given this angle to be theta. Well, as you can see, the tension is applied with an angle with respect to x and y, so let's decompose that, find the y component, and find the x component of this tension. So if this angle is theta, then this angle is also theta. Then the y component of the tension, t sub y, is t cosine theta. And tx, then the x component of tension is t sine theta. Now, if we write the net force acting on this body in the x direction, then we have F sub e in the positive x direction, we're taking it as positive, minus t sine theta because it's in the negative x direction. Since the pendulum is not swinging anymore, it's in equilibrium, then the right-hand side has to be equal to 0. The net force acting on it is 0. From here, the electric force is going to be equal to t sine theta. All right. Now, the net force in the y direction is t in the y direction, positive y direction, minus F sub g. Again, the pendulum is in equilibrium in the y direction, so it's going to be equal to 0. T cosine theta equals F sub g. Now we're going to combine these two solutions. T sine theta equals Fe. T cosine theta equals F sub g. The easiest way to do it is to take the ratio of these two equations. Left-hand sides and right-hand sides, tensions are going to cancel out. Tangent theta is going to be equal to Fe over F sub g. Well, you might as well, instead of doing this, you can isolate T out of the first equation and substitute in the second, and you're going to get to the same equation that we have here. Now, F sub E then is going to be equal to F sub g times tangent theta. F sub E, again, due to the electric field, external electric field, so that equals to Q times E. F sub g is the gravitational force, and G tangent theta. So if we want to know what the magnitude of the charge is, we can divide both sides by the magnitude of the electric field. Then Q is going to be equal to mg tangent theta over E. Now, we know what m is. It's given to us in the problem as 1 gram. We know what gravitational acceleration is. It's 9.8 meters per second square. We know the strength of the electric field. It's given to us as 15,000 newtons per coulomb. However, we're not directly given the angle, so we have to find the angle. The easiest way to find the angle is go back to this figure here. You see how from the equilibrium point, the distance the, without any electric force to the equilibrium point is 12 centimeters. So as you know, this is also 55 centimeters, right? This is the string, where the string would go if we didn't have this external electric field. So then 55 minus this 12 then gives us the side length of this triangle, right? So now we have this triangle. This is 55 centimeters. This is 15 minus the side is 15 minus 12, and this angle is theta. 15 minus 12 is 43, right? So now, how are we going to figure out what this angle is? The easiest way to remember is, I guess, the definition of cosine theta. Cosine is adjacent 43 over hypotenuse 55. So if we take the inverse of this ratio, this should give us our angle. So if you do this, you're going to figure out the angle to be 38.6 degrees. Now, going back to our main equation, now we're going to plug in for the numerical values. 1 gram is 1 to times 10 to the power negative 3 kilograms. G is 9.8 meters per second squared. Tangent, we calculated it to be 38.6 degrees divided by 15,000 newtons per coulomb. From here, we find the magnitude of the charge to be 5.2 times 10 to the power of negative 7 coulombs. And remember, this is a positive charge.